look at it as a norm vector space, taking the sup norm, saying that the norm is a sup of the coefficient. So now the multiplication map is very easy. It's a norm 1 because it doesn't change the coefficients. The evaluation map, maybe it can collapse a bit of coefficients because you have sums in the Archimedean place. It's not going to increase the norm of the size of the coefficient. So the norm is going to be less than what the triangle inequality gives you. And it will keep the degrees. Okay? So now you have the divided difference. Divided difference is a norm 1 map because you have added a fake variable. So the norm does not change. So this is perfect. And now you have change of variables. Remember that the kernel has t minus alpha. So you want to go for t minus alpha. So here you have just a binomial expansion. So the norm is going to be less than 2 to the power n. And finally, you differentiate. When you differentiate, you have factorials. So the norm is less than the absolute value of the factorials. And when you integrate, you divide by some powers. So you divide by the power of the largest degree. So the norm is going to be less than the largest. So it's going to be a periodic contribution because at the Archimedean place, it's going to be less than 1. And it's going to be, at worst, the LCM of the denominators for the periodic values. Okay, and all these linear maps act diagonally, so you don't have a huge complication, and they conserve homogeneity. So now you remember that this was the definition of P, and this was the definition of P and L, and each of these functions we have computed their norm. So we know the norm of these polynomials. We have no work to do. And you get immediately that the norm of this polynomial is less than, so this Rm log 2 comes from the binomial expansion. This comes from the divided derivatives. And the PID contribution comes from the fact that you integrate and you have shifted derivatives. Okay. So you have the norm. It's a elementary computation, 2 lines computation you don't have to worry about. You don't need to perform saddle point and all control integrals, and you have good estimates for your functions. Now the remainder. And similarly, the remainder is treated as with linear algebra. The remainder is in fact a sum, a series of these phi's, which are linear operators, shifted by some power. So again, you can compute the norm, and then you just use a geometric series estimate to evaluate the norm. And you have precisely exactly the same constant that comes in, coming from the binomial expansion and the denominators for when you integrate. And here you recognize norm of alpha divided by beta to the power n. This comes from the geometric series expansion. And finally, this term, alpha to the power Rmn, comes from the fact that you have a homogeneous polynomial of precisely the same degree. So the constant in front of your geometric series expansion is the norm of alpha to the appropriate power. And so the quality of the approximation is pretty good. You have alpha divided by beta to the power n plus 1. So you see this number is very small if beta is very large compared to alpha. And this is all you need to know. Okay. So now we want to use, in fact, the criteria for Michel-Laurent. So remember that the criteria of Michel-Laurent, you wanted to have a linearly independent vector. So the only reasonable way to have a linearly independent vector is to have a matrix which is invertible. So you know that at least one of these linear combinations will be non-zero. So what we say is that we have a sequence of matrices which are invertible. So you know the norm of the matrix is good, and each of the lines of the matrix approximate your numbers. And you have a control on the norm and on the quality of the approximation. Provided you have that what happens is that you have precisely linear independence and a measure. a measure of independence. Okay, so now I comment on the things. So you have taken all the places together. So you have you want the norm of the matrix at all the places. If they are not integers anymore, so you need to use the product formula. So you have an upper bound for that, and you have a bound for the quality of the approximation. So what is going to happen? You are going to say, you are going to specify your place V0. You have this that is playing for you. And against you, you are going to have Fv of n over all the places. Okay? So you are going to need to sum all these Fv of n, the contributions of the norm, that is against you, and the quality of and you are going to ensure linear independence as soon as this number A is bigger than the sum over all the places of Fv of n. Okay? And you just assume that you had an integral matrix if the coefficients were rational integers, and V0 is the usual Archimedean place. The Fv of n, it would be essentially 1. You could forget of that, and you would simply say that this needs to be big enough, small enough, that goes to 0. This is Michel Laurent. Okay? And because you have A times n, if A is strictly positive, A times n goes to 0, to minus infinity, so the exponential goes to 0. Okay? And so your natural condition is that the metric property, the closeness that you have at your given place needs to be better than all the thing that you have at all other places. The proof is elementary. It's not difficult. Basically, it's the same proof as Michel Laurent's lemma, except that you compute. And it gives you for free a measure of irrationality. And once the computation are done, it gives you something like that. So the quality of the approximation plus u, that's the denominator of the approximation, divided by v. V is, if I remember properly, is the difference, is the number that needs to be positive. So you have the measure. Okay. So now what do we have? We have approximation. So we have proven with linear algebra, we have proven that we have a very good approximation. That is our Ri's. So inequality 5 comes from this lemma. Yeah, this lemma. This is inequality 5. If beta is very large compared to beta, you have a very good approximation, right? Then inequality 6 or 4 for that matter, because 4 is a special case of 5. So let us concentrate on 5. What is 5? It's the norm of these polynomials, P and L. Okay. And so you know that you have denominators, LCM of the integers that you are going to look, and the log of the, because of the shift, the rational shift that you have taken. So you have a small deformation like that. So you have this number, and the Archimedean contribution, which is simply this coming from binomial terms, right? Recall that the binomial comes only from the kernel because you have t minus alpha in the definition of B, where is the polynomial B. B and L is here. Where I put it here. It's even before. This is your kernel function. Yeah. Your B is this polynomial inside the big parenthesis, t to the power L, t minus alpha to the Rn. Okay. And when you expand t minus alpha to the power Rn, you have binomial exponents. Okay. This is where you lose. Okay, so we have a good estimate. So we know everything. We know how to sum. We know that we are going to have linear independence. So our big trouble will be, in fact, this condition. the matrix needs to be in GLM. Okay, so the matrix needs to be invertible. So that means that this determinant needs to be non-zero. So this is the last part of the thing, and it is not the easiest one. So I go show you again the formula. Yeah, here it is. So you have a huge Rmn cross Rmn determinant with n going to infinity. Each of the entries is like that, right? And you need to show that the determinant is non-zero. So here you have a bit of a challenge because, in fact, in algebraic geometry, we have zero estimates. People like Bonoel, Masser, Filippo, and Nesarenko and others have developed tools to help you show that strange things cannot be zero. Here you are just linear algebra determinant, and it's not apart from the few elementary things that we have learned in the calculus and linear algebra class in the undergraduate school, we don't have so many tools. So we need to develop a few tools to approach that. And we need to actually show that this determinant is non-zero. This is the last challenge. So I'll sketch the argument. We still have a couple of minutes.
Yes, you have 10 minutes.
10 minutes. Okay, so I need to go. So I go to the non-vanishing. So this is our matrix, PNL and PNLI. Okay, huge matrix. So the first thing to do is, the first thing that I claim is that in fact this is a constant number. It does not depend on Z. So how do you perform that? You see, remember that PNL, PNLI approximate your thing. So if you perform line and column shift, you are going to have the remainders in all the other lines and just one line with big polynomials. And the remainders are in 1 over Z to big power. So they are going to have a negative valuation in Z. So if you make a valuation computation of that, you see that the valuation of this is in fact this big polynomial. You just shift, you put the remainders all over here. You see that in fact it's a negative valuation, but it has to be a polynomial by definition. So it has to be a constant. Okay, first step. So you go and chase for where you are going to have the constant. You identify the minor which is able to give you a constant, and you reduce to that. First step. Once you have done that, you fix your notation. You have your kernel. You write down the thing, and again you make a couple of manipulations of line and column that I'm going to skip because time is running short. But they are not so easy to do. So what you do is that for each line, you introduce a fake variable. You replace this t by a tis for each line, different variable. So here you perform the same idea as you perform when you compute a Vandermonde determinant. You treat each of the entries of the Vandermonde determinant as an independent variable so that you can perform a degree computation. So you do that inside of that. You have your fake variables. And you see that, in fact, you identify your vectors as one of your function phi. Phi is an integration, right? Composed with some divided derivatives and some other things. So it has a precise definition. So it is actually a linear operator applied to one fixed polynomial, which is a kernel function. So once you have that, you can do some algebra. So you compute the polynomial, it comes from the kernel, so it's just the same kernel that you have split in false variables, it becomes a polynomial of several variables, and you have your linear operator of sum. So you study that, and you see that in fact, 0 is going to be a factor at a huge power. So you just chase the zeros, and you show that this, in fact, so the next step is going to prove this one. In fact, the strange thing is that this huge polynomial factorizes basically as an Hermite, as a Vandermonde, an Hermite determinant. Vandermonde with some multiplicities. So what you do is you identify the first factors. This is done by elementary approach. And then your challenge is to prove that the polynomial is divisible by the difference alpha I, like in the Vandermonde, with the right exponent. So what you do is you show that it's a homogeneous polynomial, and these factors are trivial roots. Once you prove that these factors are trivial roots, you just need to find these roots. So if you just specify two lines, alpha 1, say alpha 1 and alpha 2, you need to say that if alpha 2 specializes to alpha 1, the determinant vanishes with this multiplicity. So you need to differentiate this determinant to this power and show that it's actually equal to 0. Okay? So this is the last step. So for the last step, what you do is you recall that psi is a primitive. You differentiate a primitive, so basically it should cancel out. It does not commute properly, but you have to take into account these things. And in the beginning itself, in the kernel polynomial, you have a huge root. Where is the kernel polynomial? You have huge roots. So if the variable happens to be another alpha I, it's going to be 0 at this huge power. Okay. So you already know that you have multiplicity, this thing. And the thing that is bad for you is that, in fact, you don't differentiate. If you were just differentiating, it would be easy. But in fact, you're primitive. Psi is a primitive. And when you get primitive, you lose 0. So what you should do is to show that you have cancellation between primitives and differentials. So this is usually fine. Only thing is that you have low order things where you have some primitives that remain, and then you must use some symmetry argument. Once you use the symmetry argument, you kill the small factors, and actually you can show that you have this. And the last step is, so where is the thing? Yeah, this constant C and UN. You have factorized, and you need to show that the constant is not 0. Okay. And in fact, the constant is basically the integral of a real function in the hypercube 0, 1. So this is something like that. And then it's undergraduate mathematics. You can show that it's non-zero by sign manipulation. And then you have shown that the determinant is non-zero. Okay. Maybe I can use a couple of minutes to comments. Michel, how much time do you allow me?
You have 4 minutes. It's okay?
Excellent, excellent. So I want to go back to the question of the shifts varying freely. So when the shifts vary freely, what happens? Construction of Madé, because we have a formal construction, is going to go through verbatim. You have no issue of that. Okay, no problem. Size approximation. This is an issue because if the shift becomes irrational, your large function is not a G function anymore. So in fact, you have no chance of having a good quality approximation. So you need, if you want to have a good quality approximation, if you want to use this kind of methods, you need to assume that xi's are rational numbers. Okay, otherwise it's a different set of ideas that need to be developed. So X to be rational is a necessary hypothesis for this approach. And then non-vanishing. And non-vanishing, the determinant, it becomes significantly more complicated because your primitives are shifted and all the things that I've described there are very delicate and they are not a complete machinery yet. Nevertheless, it works. And nevertheless, strangely enough, it remains an Hermite determinant even if the xi's are different. But this is even longer. The first proof is more than 10 pages long, and this is even longer. And it will be described in the next, we have not yet finished the write-up. It's going to be, but it's actually still is a Hermite determinant. So I think that the next step is to prove a systematic way of showing that all these methods always take you to Hammett determinants, in which case you would have a general zero estimate kind of approach. Voilà. Merci, Michel. Merci. Thanks.
Yeah. So, thank you very much. So, thank you, Sinu. I think the non-vanishing of the determinant is a very impressive step, and even you say that you can expand it. I wonder whether it's possible to state some general result which could be used in similar circumstances, because it looks like a very deep.
I think so.
Step.
I think so. But for the time being, the first proof was very ad hoc, and in fact, we first looked at the formulas. We tried to do it, and of course, we could do nothing. And that's how. That's when Makoto came up with a more formal approach that we could make a breakthrough and show that it's actually not vanishing. Now we have modified the proof. It's still a bit ad hoc, but I think that we are not very far from trying to have something that tells you that in some sets of situations you are going to have an Hammett determinant. Because the fact that the determinant is not zero, it's not easy to prove, but the fact that it's actually an Hammett determinant is very surprising.
Yes.
That so it's a very standard thing, and the fact that it comes out, it doesn't move when X varies, is as you say, it shows that there is something behind.
Yeah. So the formal approach shows that it is very powerful.
Yeah. And okay. You see, even the analytic computations become easy.
Ah, yes. Yeah. Okay. Thank you very much. Are there some questions?
Yeah.
Yes, please. Someone, there is some question?
Yeah, and I would thank Philippe for translation.
Yes. Divided difference. Yeah. Thank you. Okay, so let me thank the three speakers of this morning. We had a very interesting set of three talks, one after the other. So thanks to all of you, and you can relax now for some time. I don't know when is the next session, but so have a nice day, and thanks again. Bye-bye.
So I would like to,
yeah.
So I would like to thank Professor Waldschmidt for chairing the session, and we meet in 40 minutes.
Happy birthday, Balu.
Oh, thank you. Thank you.